For our second objective, you'll be able to find the area of a plane region using a Riemann sum. By a plane region, I'm talking about, let's say, you take a look at this picture over here, this graph, this is the natural log x, and let's say that I wanted to find the area underneath that curve right there. That's a plane region, and of course there's no particular formula for it, but we can use calculus, and particularly a Riemann sum, in order to find it. The image here of this totally exhausted guy in the deserts just wanting a glass of water, it refers to the method that we use to find the area of that plane region called exhaustion. So you might remember at the beginning of the year we discussed two major problems that led to the development of calculus. The first one was the tangent line problem, which gave us differential calculus, and the second one is the area problem. And the solution to the area problem gives us integral calculus, which is what this whole entire unit is about. So more or less, what we want to do is we want to find the area underneath some nonlinear curve bounded by the x-axis, like what's in the diagram. And you can definitely see that it's not like it falls into a category of some geometric formula that we know. So how do we tackle it? How do we find the area underneath that curve? And so the solution involves breaking it up into rectangles. So if I can break this thing up into rectangles, and notice that the height of the rectangle, of each one of these rectangles, is just basically a function value over some sort of width. Now, of course, that's not a perfect area. It's not the exact area underneath the curve, but it's at least a pretty good approximation. And you can improve this approximation by making the width of each one of these rectangles as close to 0 as possible. That sounds sort of like a limit, right? As the width of those rectangles approach 0, we're going to get closer and closer to the actual area underneath the curve. And once again, that process is called exhaustion. And it's like the first instance of it, we can think of Archimedes' method of approximating pi. You might remember back in geometry, we did a little project on approximating the value of pi. And pi is supposed to be the ratio of the circumference of a circle to the diameter of that circle, which is really hard to measure. So instead, what Archimedes did is that he broke it up into a series of polygons. Polygon on the outside and a polygon on the inside, because you got straight sides. Those things are easy to measure. And so he got closer and closer and closer to the circumference of that circle by breaking it up into smaller and smaller pieces, thereby getting closer to the value of pi. Archimedes, of course, is the person who said that pi is approximately 3.14, and of course that's stuck around, and that's probably the first approximation you ever heard about it in like the 6th or the 7th grade. Did the same thing with the area of the circle as well, breaking it up into smaller and smaller pieces based on, let's say, the area of some sort of polygons. Okay, so we're going to use this kind of idea of breaking it up into smaller pieces, smaller and smaller pieces, getting closer and closer to 0 in order to find the area underneath a curve, which we'll call a plane region.